All right, chapter 2 is on atoms and elements. I'm going to start with this slide. I don't really go into the history of atomic theory. You know, it's kind of boring. So this video kind of takes care of, I don't know, goodness, like 2,400 years of atomic history. So
what do an ancient Greek philosopher and a 19th century Quaker have in common with Nobel Prize winning scientists? Although they are separated over 2,400 years of history, each of them contributed to answering the eternal question: what is stuff made of? It was around 440 BCE that Democritus first proposed that everything in the world was made up of tiny particles surrounded by empty space. And he even speculated that they vary in size and shape depending on the substance they compose. He called these particles atomos, Greek for indivisible. His ideas were opposed by the more popular philosophers of his day. Aristotle, for instance, disagreed completely, stating instead that matter was made of 4 elements: earth, wind, water, and fire, and most later scientists followed suit. Atoms would remain all but forgotten until 1808, when a Quaker teacher named John Dalton sought to challenge Aristotelian theory. Whereas Democritus's atomism had been purely theoretical, Dalton showed that common substances always broke down into the same elements in the same proportions. He concluded that the various compounds were combinations of atoms of different elements, each of a particular size and mass, that could neither be created nor destroyed. Though he received many honors for his work, as a Quaker, Dalton lived modestly until the end of his days. Atomic theory was now accepted by the scientific community, but the next major advancement would not come until nearly a century later, with the physicist J.J. Thomson's 1897 discovery of the electron. In what we might call the chocolate chip cookie model of the atom, he showed atoms as uniformly packed spheres of positive matter, filled with negatively charged electrons. Thomson won a Nobel Prize in 1906 for his electron discovery, but his model of the atom didn't stick around long. This was because he happened to have some pretty smart students, including a certain Ernest Rutherford, who would become known as the father of the nuclear age. While studying the effects of X-rays on gases, Rutherford decided to investigate atoms more closely by shooting small, positively charged alpha particles at a sheet of gold foil. Under Thomson's model, the atom's thinly dispersed positive charge would not be enough to deflect the particles in any one place. The effect would have been like a bunch of tennis balls punching through a thin paper screen. But while most of the particles did pass through, some bounced right back, suggesting that the foil was more like a thick net with a very large mesh. Rutherford concluded that atoms consisted largely of empty space, with just a few electrons, while most of the mass was concentrated in the center, which he termed the nucleus. The alpha particles passed through the gaps, but bounced back from the dense, positively charged nucleus. But the atomic theory wasn't complete just yet. In 1913, another of Thomson's students by the name of Niels Bohr expanded on Rutherford's nuclear model. Drawing on earlier work by Max Planck and Albert Einstein, he stipulated that electrons orbit the nucleus at fixed energies and distances, able to jump from one level to another, but not to exist in the space between. Bohr's planetary model took center stage, but soon it too encountered some complications. Experiments had shown that rather than simply being discrete particles, electrons simultaneously behaved like waves, not being confined to a particular point in space. And in formulating his famous uncertainty principle, Werner Heisenberg showed it was impossible to determine both the exact position and speed of electrons as they moved around an atom. The idea that electrons cannot be pinpointed but exist within a range of possible locations gave rise to the current quantum model of the atom. A fascinating theory with a whole new set of complexities whose implications have yet to be fully grasped. Even though our understanding of atoms keeps changing, the basic fact of atoms remains. So let's celebrate the triumph of atomic theory with some fireworks. As electrons circling an atom shift between energy levels, they absorb or release energy in the form of specific wavelengths of light, resulting in all the marvelous colors we see. And we can imagine Democritus watching from somewhere, satisfied that over 2 millennia later, he turned out to have been right all along.
All right, so that's 2,400 years of history in 5 minutes. So there are some laws that led to this development of modern atomic theory. The first one, this was really big in Dalton's work, was the law of conservation of mass. Law of conservation of mass states that in a chemical reaction, matter is neither created nor destroyed. So if I start a reaction with 19.6 grams of reactants, I will end that reaction with 19.6 grams of products, always, which you can see in this picture here. So when a log completely burns in a campfire, the mass of the ash is much less than the mass of the log. What happens to the matter that composed the log? We know it can't disappear. It can't cease to exist because of the law of conservation of matter. So that's actually a type of reaction called a combustion reaction. And what happens is that a lot of the products of a combustion reaction are gases. And so they just kind of go off into the air. If we were to trap those gases and weigh it along with the ash, it would weigh exactly the same as the log weighed before we burned it. The next law is the law of definite proportions. The law of definite proportions states that all samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. So we talked about this last chapter when we talked about compounds and how, water is always H2O, and it doesn't matter what sample of water you have, where that sample of water is in the universe, it is always H2O. Carbon dioxide is always CO2. Same thing, right? It's always 1 carbon to 2 oxygens. And so this is just a quick video to show how we know that water is H2O. It's going to be electrolysis of water, which is taking the H2O and splitting it apart into hydrogen and oxygen and capturing the gas in the test tubes. So you can see here.
What we're going to do is we're going to take 2 different test tubes here. And each test tube has a metal wire kind of running up along it. We're going to just barely place it over that metal lip. Spin that around so that you can see it nicely. What we're going to do is we're going to take that and hook it up to the negative and positive terminals of a battery. So the black there to the negative, and the red there to the positive. When we do that, we see 2 different gases being produced at different rates. What we're going to do is we're going to look at how much of each one we get and what each one is. I'm going to go ahead and zoom in and speed this video up so you can see that go a little faster. So now getting to the point where at about 10 milliliters in here and at about 5 milliliters in here. Hopefully you could have seen that there was a 2-to-1 ratio of the 2 gases the whole time, this one being twice as much as this one. All right, I'll zoom back out and kind of see what the identity of these 2 gases are. So to do that, we're going to do a little splint test. I'm going to let the reaction keep going while I test this one here because I want this one to fill up a little bit more. So first thing I'm going to take this tube, get out the solution. Okay, so that right there, that little mini explosion there, is indicative that we had hydrogen gas at this end of the container. So we had twice as much hydrogen gas as whatever the gas is that's in the other component of this. So I'm going to let that run for a little bit longer. We'll go ahead and speed this back up again. We'll come back and check out where that is. Okay, so we're now at a point where we can go ahead and test this. So to do that, I'm going to take a splint, ignite it. Sorry about that. Just like that. And we're going to go ahead and put that out. And we're going to use that to test this. Okay. So we can see there that, get that candle out of the way. Splint reignites in there, which indicates that there's oxygen present inside of that tube. So what we're showing is that we have 2 times as much hydrogen gas being produced as oxygen gas over here.
All right, so I know like water's H2O, right? Duh. But somebody had to figure that out. And experiments similar to this is how they figured that out. And we can show that water is always H2O. You know, if we run this experiment 10,000 times, each time we're going to get twice as much hydrogen as we do oxygen. So that's your law of definite proportions. A couple problems with law of definite proportions. So ammonia is 14 grams nitrogen for every 3 grams of hydrogen. What is its mass ratio? So I would just do 14 grams nitrogen, divide that by 3 grams hydrogen, and I'm going to get 4.67 grams of nitrogen for every 1 gram of hydrogen. So a sample of ammonia contains 10 grams of nitrogen. Nope, that's supposed to say, let's just change this to hydrogen, I guess. 10 grams of hydrogen. How many grams of nitrogen does it contain? So if my ratio is 4.67 grams of nitrogen to 1 gram of hydrogen, we can then just extrapolate that, right? This would be 10 times as much. So the grams of nitrogen would be 10 times as much. It would be 46.7 grams of nitrogen to 1 gram, or 10 grams of hydrogen. All right, law of multiple proportions is the last one. So the law of multiple proportions states when 2 elements A and B form 2 different compounds, the masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. So that sounds complicated. Basically, it just means that 2 different elements can sometimes form many different compounds. So the law of definite proportions is like water is H2O, period, end of story. It is always H2O. Law of multiple proportions is that oxygen and hydrogen can combine in different ratios, but it will always be small whole numbers. So like hydrogen peroxide is 2 hydrogens to 2 oxygens. So if carbon monoxide has a mass ratio of 1.33 grams oxygen to 1 gram carbon, and carbon dioxide has a mass ratio of 2.67 grams oxygen to 1 gram of carbon, you can actually show that this supports the law of multiple proportions by taking those masses. So we're going to take the mass of oxygen to 1 gram carbon in carbon monoxide, and the mass of oxygen, over the mass of oxygen to 1 gram of carbon in carbon dioxide. So that's going to be, I should have done it the other way to get a whole number, but whatever, it'll still work. 1.33 to 2.67, which is going to give you, when we reduce that, 1 to 2. So small whole numbers. So that's how it would always work. You would take it to like 1 gram of the carbon and then just show that they obey the law of multiple proportions by getting the ratio of the masses to 1 gram of carbon and showing that that ratio is small whole numbers. All right, so that is the law of multiple proportions, and that is it for today.